Hello everyone, this is Kenny from Cambridge Tech and welcome back to the channel. Now if you are watching this video, bear in mind this is the part 2 of a NumPy series and this is going to be the last part actually. So you probably may need to watch part 1 if you are entirely new, and the link will be in the description below. So in this particular section we are going to look at some arithmetic operations that we can do with NumPy. So let's say we have, and let me put out a cell over here at the very top. And let's have some two arrays that we are going to use to perform these mathematical operations. Let's say we have an x which is np.array, and let's put out some array over here. So we have 1 2 3, and let's have y, and y is going to be np.array, and let's just change things up a little bit over here. So we have 7 3 1 over here. So these two arrays are what we are going to work with. All right, so let me run this with a shift enter, and here we are. So in addition, or in all these operations that we are going to look at, is going to be an element wise operation. So what this basically means is, if I'm to add the array x and y, it is going to add them element by element. So it's going to be 7 plus 1, it's going to be 3 plus 2, it's going to be 1 plus 4, 1 plus 3. So one way of doing it is basically, let's say I have a variable z can be just x plus y, and when I print out z, you can see that this is the element wise operation that I was referring to. So this plus this is going to give us 8. This plus this is giving us 5, and 3 plus 1 is giving us 4. So this is one way of doing it, and let me just comment this one out. Alright, so let me just run this so that it clears everything up over here. So to use the NumPy way, we can use np.add. So when I do np.add, I can just pass in the arrays that I want to add, and when I run this, it is definitely going to give me the same results as this. Okay, so this is the NumPy way of doing things. Now let's look at subtraction. I can do np.subtract. So when I do np.subtract and do x comma y and run this, you can see that yes, the subtraction operation has been carried out. And bear in mind, it is going to look at the order. So in this particular order, it's going to be 1 minus 7, which is going to be negative 6. 2 minus 3 is going to be negative 1, and we have 3 minus 1 is going to be positive 2. If I'm to change the order y and do an x over here and run this, it is also going to change everything, and we are going to see this. Now let's look at multiplication. If your guess is as good as mine, we can do np.multiply. So when I do np.multiply and pass in y and x as we have it over here and run this, you can see that 7 times 1 is giving us 7, 3 times 2 is giving us 6, and obviously 3 times 1 is also giving us 3. So now let's look at addition. So I can do np.divide and pass in x and y, and now when I run this, we are seeing this. Obviously, remember, we are getting some floats over here. So we have x, which is this 1 divided by 7, and this is giving us some floating point value, and 2 divided by 3 is also giving us this, and obviously 3 divided by 1 is giving us 3. So that's exactly what you have over here. You can look at the square roots as well. So the square roots is going to be np.sqrt. So sqrt stands for square root, and over here we can pass in 2 arrays. We just have to pass in 1. So for instance, we want to find the square roots of each element in this particular array, and if I'm to run this, we have 1. The square root of 7 is what we have over here, and the square root of the square root of 2 is what we have over there, and the square root of 3 is showing up over here as well. Then we can also look at the dot product. So I can do np.dot, and we can pass in an x and a y, and when I run this, we have this showing up over here. So the dot product, so this is going to give us a 7 times 1, which is going to give us a 7. 3 times 2 is going to give us a 6, and 3 times 1 is going to give us a 3. So it's going to be 7 plus 6 plus 3, and that's what we have over here as 16. Now you can also check out for LCM and GCD. So once again, let me also put out a new cell over here, and let's have x is, let's say, 92, and y is 15. Want to look out for the LCM of x and y, so we can do np.lcm, and we just pass in x comma y. And when I run this, sorry, I need to run this first, because as you can see, it is not run. So I'll run this, and when I run this, you can see that the LCM of these two numbers is what is being provided over here. You can also look at the GCD. So I can do np.gcd, and I'll just pass in the value x and y, and when I run this, the GCD is going to be 1. All right, let me change this to, let's say, probably 30, or yeah, let's say 45. So let me run this. The LCM is now 45, and the GCD is 15. All right, so now let's look at broadcasting. Broadcasting is obviously some of the mathematical operations that we can do with NumPy. So in this very example, you can see that we can have, this is a vector, obviously. We can have a vector and multiply a scalar quantity by it. So this is a scalar quantity. This is just one element. And what this is going to do is it's going to multiply each element of it as we see over here, and the result is what we have over here. So in this particular image, you can see that we have 2 times 1, which is going to be 2. We are also going to have 2 times 2, which is going to be 4, and 2 times 3. Let's look at it in real life. So let me just run this over here, and let's just have np.array, and let's just have 1, 2, 3. Let me save this as x, and let me have also y, and y is equal to the example 2 we have over here. So if I run this, we don't seem to have any problem over here. Let me bring out a cell over here. So over here, I can just do x multiply by y, and when I run this, that's exactly what you have over here. We have 2, 4, and 6. So it's going to perform the element wise multiplication. So this times this, this times this, and all that. Okay, now there's also one thing I would also want to touch on, and probably I should have done this earlier, but then let's move on and I'll come back to it. So within the element wise operation, we can also do addition. So as you can see, this is a 4x3 matrix. As you can see, it has 4 rows and 3 columns, and we have a vector over here with 3 elements. Now if you do an element wise addition, as you can see over here, this is also going to work. But when there's a mismatch in terms of the pairing, then there should be a problem one way or the other, because as you can see over here, you have 4x3, and this is a vector of 4. So let's assume the first one matches with the first one, the second one matches with the second one, the third one matches with the third one, and the fourth one will not have any match over here. Because with this particular example, you can see that you have 0, 0, 0, and plus 1, 1, 1. So this 1, 1, 1 will be added onto this, and that's what you have over here. The 1, 1, 1 will be added onto the second row, and that's exactly what you see over here onto the last row. And in this case, there'll be a mismatch. So this is definitely going to give us an error. All right, now let's look at some linear algebra computations that we can do with NumPy. And this is very important because as data scientists, as engineers, probably you may come across some of these things. Now let's look at the transpose of a matrix. So let me just have a matrix X, and let me have this as np.array, and let me have a 3x3 matrix. So I'm just going to have 1, 2, 3, comma, and I want to have 4, 5, 6, and last but not the least, I would want to have 7, 8, 9. And let me just print this out over here. All right, and let me put out a cell over here, and let me just check the shape. So I'll do x.shape And yes, this is a 3 by 3 matrix. So what a transpose basically means is, with this particular matrix, we want to change this first column. If I transpose this matrix, will now become the first row. So instead of having 1 2 3 lined up this way, we are going to have 1 2 3 lined up in a vertical cross section, and you're also going to have 4 5 6 line up as the second column over here, and 7 8 9 will also be lined up as the third column over here. And in order to do this, there are actually two ways. We can do x.t. So when I do an x.t and run this, as you can see, this array over here or matrix has been transposed. And that's exactly what I was referring to. So 1 2 3 is now 1 2 3 in this column, and 4 5 6 is now 4 5 6 in this column, and 7 8 9 is now 7 8 9 in this column. Now there's one way of doing it, and let me show you another way of doing it. So let me bring this out over here, and this is the NumPy way of doing it. So I can do np.transpose. So I just do np.transpose and passing the matrix over here, and when I run this, we are getting the same value over here. Now let's look at the inverse of a matrix, and this is very important, and these are some of the reasons why NumPy is faster than just using list, because the methods are there, you just have to use them, and this can come in very handy. So let's say you want to find the inverse of this matrix, and before I continue, let me say that in order to find an inverse of a matrix, the matrix must be a square matrix. Okay, so the matrix must be a square matrix. I'm getting the spelling of square wrong. So square matrix, and what this basically means is, remember, you see this shape 3 by 3. This is a square matrix, so it should either be a 2 by 2, a 3 by 3, a 4 by 4. So the number of rows should be equal to the number of columns. That's basically what this means. But even before we deal with the inverse, let me just bring this up, and yeah, let's look at the identity matrix. Yes, we are definitely going to talk about the inverse, but I feel the identity matrix should maybe come first. So an identity matrix is a matrix that has the diagonal as 1. Okay, so this is a diagonal, or the main diagonal. So the element in this particular matrix has 1 5 and 9. An identity matrix will have 1 1 and 1, and everything apart from the diagonal matrix is going to be 0, and it should also be a square matrix as well. So I can do np.identity, and I'll just need to pass in the kind of matrix that I want. So if I just do 3, that means I need a 3 by 3 matrix. So when I run this, all right, so I think there's a mistake over here. It's supposed to be identity and not identity. So when I run this, as you can see, this is the identity matrix I have over here. Now if I'm to change this to a 2, when I run this, you can see that I have 2 over here. If I'm to do a 4, I'm just having an identity matrix of 4. Now as you can see, obviously the elements over here are represented in floats. Clearly we can change some few things. So I can have let me put out, yes, this over here. So this is 4, all right, but I can do a D type. Remember when we change the type to an int, so I can do a D type, and I'm just going to type in an int over here. And now when I run this, you can see that the identity matrix is well shaped and everything is looking great over here. All right, so now let's look at the inverse of a matrix, and this is, this involves some level of calculations. If you've worked matrices with your hands before, you definitely know that some of these things can be a daunting task. Now you already have this matrix over here, which is the x, and that's what we are going to work with. So let me just copy x. Let me just copy x as you have it over here. So I'll do a Ctrl+C, and I'll bring it down over here, and I'll paste it over here. So this is our x. We want to find the inverse of this matrix. Let me bring this cell up over here. So to find the inverse of this matrix, there is a sub package in NumPy that deals specifically with linear programming. or linear algebra. So what I can do is I can do np dot, this is linear algebra, so this LIN stands for linear and ALG stands for algebra. So I can do linear algebra, and now I can do dot, and I'll do inverse or INV, and now I need to pass in the matrix over here. So I'll pass in X, and now when I run this, I have the inverse showing up over here. Very nice. Like I said, if you have worked with matrices by hand, you know that this is actually a miracle, because working out this is a very long process. All right, so this is very cool, and we can use this. Now we can also calculate, or we can use NumPy to calculate the eigenvalues and eigenvectors. And like I said, if you're an engineer and you work with some of these mathematics, you know that it is very important doing it this way. So over here, we are also going to use this same matrix to calculate for the eigenvalues and eigenvectors. So what I'm going to do is I'm going to do np dot, once again, the linear LIN, the algebra ALG, and I'll do dot. So the eigen will be EIG, and I need to pass in X over here. It is calculating, so as you can see, it is running over here. Now, it took a while for it to calculate, and we are getting some things we are not quite familiar with. But then what it basically does is it returns this array, which is the eigenvalues, and another array over here, which is the eigenvector. So we can do some multiple assignments over here. So we can do eigen, so e dot values, which is going to be the first returned over here, and we can do the eigenvectors, so e dot vectors over here, which is going to be equal to this. So now we can print them one after the other. So I just want to print out the e values, which is the eigenvalue. So now when I print this out, this is the eigenvalues over here, and let me print out the eigenvectors over here too. So I'll just copy this, Control C, and print it out over here. And as you can see, this is the eigenvectors. And once again, this can be a lifesaver because it cuts out a lot of work and computations. Now you can also check out for the determinant of a matrix. We are using the same matrix X over here. So this is also np dot the linear algebra package inside of this, and we can do determinant. So this is going to be det, and we're passing X over here. So when I run this, this is going to be the determinant of this matrix. Now the determinant, if it is a 2x2 matrix, it is a little bit simple working with 2x2 matrix, but then in a 3x3 matrix, it involves a lot of calculations. So you can have the determinant just by using this NumPy method over here. Now you can also solve some linear equations. Okay, so let's say you have this particular equation. We can transform this into a matrix, and this is exactly what we have. So when we are transforming this into a matrix, we need to bring out the coefficient. So the coefficients in this particular first line of equation, we have 1 over here and we have 2, and that's what we have. And the second equation, we have 3 and 4. So the coefficients will form one matrix, and the variables are also going to form one matrix, and this is going to be the right hand side of the matrix. Now you can check this out by solving by hand, but then NumPy gives us a shortcut which we can use in solving this. So we can do np dot, once again, the linear algebra package in here, and we can do dot solve. So when we do dot solve, it is going to solve this system of equation. And in order to even get to this point, let me just comment this one out. In order to even get to this point, we need to first write out this equation. So once again, let me just put out a cell over here and bring it up. So first of all, we need this matrix over here. So let me say I'm calling this M for the matrix, and I can do np dot array. And remember, this is a 2x2 matrix as you see over here. So I need these two brackets over here, and I'll do 1, 2, and I'll do a comma, and the next set of values I have over here is 3, 4. Now let me print out m and see exactly what I have and check if it is exactly like this. Let me also check out for the shape of my m, my matrix. So I'll do m.shape, and obviously it is a 2 by 2 matrix as we see it over here. Now the next matrix or vector I need is this column vector over here, and in order to do so, let me just put out this over here, and this is going to be like the right hand side value. So I'll call this right hand side, so RHS, and this is going to be np.array, and as you can see over here, this is just a 1D array. So I can do 6,16, and let me just print this out over here. So I'll run this and I have this showing up over here. Now let me do a dot shape over here, and clearly I also have this 2 elements in here. Now in order to use the linear programming or matrix or NumPy to solve this, all I need to do is, once again, let me just uncomment this, np.lensolve, and I just have to pass in the matrix, which is m, and the other parameter is going to be my right hand side. So I'll do a Control-C and paste this over here, and if I'm to run this, it is going to give me the x value. So x is going to be 4 and y is going to be 1. You can actually solve this and it is actually going to give you the same values. So this can come in very handy when using NumPy. We can also perform a bitwise operation using NumPy. So here we have a truth table for some digital electronics, okay, and what I want to do is, let me just have a cell over here, and let's say we have our inputs a and b. So a is equal to a high, which is 1, and b is going to be equal to a high, which is 1. Now what I want to do is, I would want to use the bitwise operator over here, and the first one I have over here is the OR gate. So for all I can do is, I can do, first of all, let me just run this cell, okay, and let me create in another cell over here. I can do np.bitwise, and I'll do an underscore or. So np.bitwise, sorry, I think my spelling of bitwise is wrong. So np.bitwise or, and I just need to pass in a and b. So when I run this, it is going to return a 1 over here, and from this truth table you can actually see that an OR operation between a 1 and a 1, the output is going to be a 1. Now let's try a 0 and a 1. So a is 0 and b is 1. So let me run this once again, and when I run this, we are also going to get a 1 over here, because a 0 and a 1, the output is 1. Now we are only going to have a 0 if both turn out to be 0. So when I do 0 0, run this and run this again, now that we have 0 over here. So we can use NumPy to perform bitwise operations. Now we can also use it to look at for the AND gates, and I'll leave it for you as an assignment because it's basically the same thing. All that you need to do is, let me just put out this over here. If your guess is as good as mine, you can just do np.bitwise underscore end, and you just pass in your a and your b. And like I said, this is going to be an assignment. You can just practice with yourself. All right, now finally, let's look at we using NumPy to convert any number from, let's say, base 10 to binary or base 2. All right, so what I want to have over here is, I want to have a variable called number, and let's say I have 90. So I want to change 90, which is by default a base 10 number, into a binary number. So all that I need to do is, I can do np.binary underscore repr, and I need to pass in number over here. Now when I run this, this is also a binary representation of 90. Now in order to make things very simple, we all know that 2, okay, the number 2 in base 2 is going to be 10, or no, yes, 10. So when I run this, now you can see that we have 1 0 over here. 3 in base 2 is going to be 1 1, and that's exactly what we have over here. So you can just look at any number 19, and we have this showing up over here. You can do the manual calculation yourself. I stated over here is we can use a with and without with. Now what this with basically does is, let's say we can pass in this, and I can do a with over here, and for the with I'm going to specify, let's say 10. So by default it's just going to return this number for me. Okay, now when I add in a with and run this, it is going to add in some padding bits so that at the end of the day everything will sum up to 10 numbers. And this can come in handy when you are working with some data that you need to add in some padding bits in order to fit in a particular space. All right, so thank you very much, and this is going to be the end of this tutorial. So NumPy has a variety of methods and functions that we can use over and over, but then it depends on exactly what you are doing and what you really want to use it for. But I can assure you, you can do a lot more with NumPy. Now, if you found value in these videos that I do, kindly subscribe to Django Tech, and don't forget to hit on the notification button so that anytime I release a video, you'll be duly notified. Also, share this video with friends and family who find this content very useful. At Django Tech, we say learn programming. You can do it. Bye-bye.